All right. Let's take a look at this LinkedIn engineering blog post
Okay.
about InSearch, their custom-built messaging search platform.
Yeah.
I think as a software engineer, you'll appreciate how they tackled the challenge of making search blazing fast while dealing with a ton of encrypted messages.
What I think is impressive is that they built this entirely new system instead of trying to shoehorn in their existing search infrastructure into
Right.
this very specific use case.
Yeah.
The blog post highlights a lot of the limitations of traditional search systems when you're dealing with this insane volume of data that LinkedIn has to handle.
Yeah, it's mind-boggling when you think about all the messages flying around on LinkedIn every day.
Yeah.
And it's all private encrypted data.
Right.
So how do they even begin to tackle this problem?
Well, they started by identifying the core challenges, I think.
Okay.
The first one being the massive volume of data.
Yeah.
Millions of users generating tons of messages constantly.
Right.
The second is the high rate of updates. New messages pouring in every second.
Yeah.
And then third, the need to maintain end-to-end encryption for those private conversations.
Right.
So with those three constraints, they kind of architect a system that is optimized for messaging search.
Okay, so walk me through this architecture a little bit.
Yeah, okay.
The blog post mentions a few key components: searcher, broker, and ingestion. What's the high-level view?
I think of it like this. So the searcher is the brain of the operation.
Okay.
It's responsible for actually indexing and searching the messages.
Okay.
The broker acts as a middleman, receives search queries and routes them to the right searchers.
Gotcha.
And then the ingestion pipeline that continuously feeds new messages into the system.
Okay, interesting. And they're using a per-member index approach.
Yeah.
That seems kind of counterintuitive.
Okay.
Wouldn't one giant index be more efficient?
Not necessarily. They recognize that most users primarily just search their own messages.
Right.
So instead of building this massive index that encompasses everyone's data, they create individual indexes on demand for each member when they first perform a search.
Okay.
And then these smaller personalized indexes are then cached in memory for lightning fast retrieval.
That's really clever. It's all about optimizing for the most frequent use case.
Exactly.
So let's get into the nitty-gritty of the searcher.
Okay.
The blog post mentions Lucene, which is a pretty popular open source search library.
Yeah.
How did they adapt it for this system?
They leveraged Lucene's powerful indexing and search capabilities, but they had to modify it to work with encrypted data. Remember, decrypting the entire message store for each search would be a performance nightmare.
Yeah, for sure.
So instead, they opted for this clever combination of RocksDB, which is a key value store, and Lucene.
Hold on. Could you explain RocksDB for those of us who haven't worked with it before? What makes it a good fit here?
Think of RocksDB as a highly performant embedded database, optimized for fast key lookups and storage. In this case, they use it to store the encrypted messages themselves. Each message is stored with a unique key, which is a combination of member ID and message ID, and the value is the encrypted message content.
Okay, so when a user searches their messages for the first time, what happens under the hood?
The searcher queries RocksDB using a prefix scan to fetch all messages belonging to that member. Then it uses this retrieved data to build a Lucene index on the fly, which is subsequently cached in memory.
And that cached index is what makes subsequent searches so fast.
Exactly.
I'm guessing this approach is particularly beneficial for power users who search their messages frequently.
Absolutely. It reduces latency for repeated searches because that index is readily available.
Right.
The blog post highlights that they achieved a 99th percentile latency of under 150 milliseconds.
Wow.
Which is incredibly fast.
That's some serious performance optimization.
It is.
I'm curious, how do they handle updates? New messages are constantly coming in, so how do they ensure the indexes stay fresh?
It's a two-step process. First, new messages are written to RocksDB with their corresponding keys. Then the searcher checks if a cached index exists for that member. If it does, the new message is added to that index, ensuring that it remains up to date.
So they're essentially updating the index in real time as new messages arrive?
Yeah, pretty much.
But what about when the system restarts? Do they have to rebuild all the indexes from scratch?
Not at all. They
Okay.
very cleverly persist the IDs
Okay.
of members whose indexes are currently cached.
Okay.
So this way, when the system restarts or a new searcher instance comes
Yeah.
online,
Right.
it can immediately load these indexes back into memory, keeping the cache warm and maintaining that like speedy performance.
All right, so they've nailed down efficient indexing and caching.
Mm-hmm.
But how do they handle the massive scale of LinkedIn's user base?
That's where partitioning and replication come into play.
Okay.
They divide the entire dataset into smaller chunks or partitions
Mm-hmm.
based on member ID and document ID,
Gotcha.
and distributing these partitions across multiple machines.
Okay.
This prevents any single machine from becoming a bottleneck
Right.
and ensures that the system can scale horizontally.
So instead of one giant RocksDB instance,
Right.
they have multiple instances spread across different machines.
Exactly.
Okay.
And they don't just stop at partitioning, they also use replication.
Okay.
Each partition has 3 live replicas and 1 backup replica.
Okay.
This is like crucial for high availability and fault tolerance.
What's the difference between a live replica and a backup replica?
So live replicas actively handle search requests.
Okay.
If one machine fails, the other 2 live replicas pick up the slack, ensuring uninterrupted service.
Yeah.
The backup replica is there for data durability.
Okay.
It periodically takes like a snapshot of the database
Mhm.
and uploads it to LinkedIn's internal HDFS cluster.
Okay.
They also back up their Kafka offsets,
Right.
which are used for tracking the position in the message stream.
Okay.
So this way, if they need to restore from a backup, they can pick up exactly where they left off.
This system is sounding more and more resilient by the minute.
It is.
They've really thought through all the potential failure scenarios.
They have.
But let's shift gears a bit and talk about how new messages actually enter this system.
Sure. That's where the ingestion pipeline comes in.
Okay.
It all starts with espresso tables.
Espresso tables.
Yeah.
I haven't encountered that term before.
I can-
Can you elaborate?
Sure. It's essentially their source of truth
Okay.
for messaging data
Okay.
to capture new messages and updates.
Hmm.
They utilize Brooklyn streams, which
Okay.
can track changes in these espresso tables.
Gotcha.
These changes are then fed into a SAMSA job
Okay.
for processing.
Okay. So SAMSA is responsible for handling this incoming stream of message data.
Correct.
What exactly does this processing entail?
The SAMSA job has a few key functions.
Okay.
First, it transforms the raw data from espresso tables into a format
Okay.
that is suitable for the searchers.
Okay.
This might involve like parsing, restructuring, or enriching the data.
So it acts as a sort of intermediary,
Yes.
making sure that the data is in
Yeah.
tip-top shape
Yeah.
before it reaches the searcher.
Yeah.
What else does it handle?
It also performs like data enrichment
Okay.
by joining the message data with other relevant data sets.
Mm-hmm.
For example, it might fetch member names
Okay.
to include in the search index, making the results more user-friendly.
Right.
And finally, it partitions the data appropriately,
Okay.
ensuring that each searcher receives only the data relevant to the member IDs it's responsible for.
So the SAMSA job is doing a lot of heavy lifting behind the scenes,
It is.
preparing the data for indexing and ensuring it's distributed correctly
All right.
across the searchers.
Yes.
Okay. And there's one more critical component we haven't touched on yet, the broker.
Yes.
Okay, so let's unpack the broker a little bit.
Okay.
You mentioned earlier that it acts as a middleman
Mm-hmm.
between the users and the searchers.
Yeah.
What exactly does that entail?
The broker is the entry point for all search queries.
Okay.
When you type a search term into LinkedIn's messaging interface, that request first goes to the broker.
Okay.
It then performs a series of operations
Okay.
to efficiently route your query and retrieve the most relevant results.
So it's essentially a search query traffic cop.
Pretty much.
What are some of the key functions it performs?
It has like 3 main functions.
Okay.
Query rewriting, scatter gather,
Okay.
and retries and re-ranking.
Sounds good.
Yeah.
Let's dive into those in the next part.
Let's start with query rewriting. The broker takes your raw search query, which could be anything from like a simple keyword to a complex phrase,
Okay.
and it translates it into something that the searchers can understand.
So it's not just passing the query along verbatim.
Not necessarily.
Okay.
It might add like specific search operators,
Okay.
boost the relevance of certain fields, or apply some other logic
Right.
based on like the type of search being performed.
Okay.
This ensures that the searchers receive a well-structured query
Yeah.
that is optimized for their like indexing and retrieval mechanisms.
That makes sense.
Yeah.
Like having a specialized translator
Exactly.
to bridge the gap between user intent and the searcher's capabilities.
Yeah.
What about the scatter-gather function? How does that come into play?
Remember how we discussed partitioning earlier?
Yeah.
The data is spread across multiple searchers, each responsible for a specific subset of member IDs.
Right.
So when the broker receives a query, it needs to distribute that query to all the relevant searchers in parallel. That's what scatter-gather does.
So it's like sending out a search party.
Exactly.
With each member of the party assigned a specific area to cover.
It's a way to leverage the power of distributed computing to search across the entire data set simultaneously.
Right.
The broker fans out the query to multiple searchers, and then it gathers the results from each searcher and combines them.
Okay, that's clever.
Yeah.
It seems like this approach would significantly speed up search times.
It does.
Especially when dealing with a large data set.
Yeah.
But what happens if one of the searchers is down or taking too long to respond?
That's where the retries come in.
Okay.
The breaker has like built-in fault tolerance.
Gotcha.
If a searcher doesn't respond within a certain time frame, the broker will retry the query on a different replica.
Gotcha. So even if one searcher is having a bad day, the search can still proceed smoothly.
Correct.
Okay, what about re-ranking? Why is that necessary?
Remember, each searcher is only working on a subset of the data.
Right.
So the results returned by different searchers might not be in the correct overall order. That's where re-ranking comes in.
Okay.
The broker takes the combined results from all the searchers and sorts them based on relevance.
Okay.
Ensuring that the most pertinent results are displayed first.
It's like putting the puzzle pieces back together
Precisely.
in the right order after searching for them in different boxes.
The re-ranking process ensures consistency and delivers a coherent set of search results to the user, even though the search was executed across multiple machines.
Yeah.
And it doesn't just stop there.
Okay.
The broker also handles pagination.
Okay.
It takes into account the user's request for a specific page of results and sends back only the relevant subset.
Okay.
This prevents overwhelming the user with a huge list of results and improves the responsiveness of the interface.
Wow. The broker is a busy bee.
It is.
It's handling query translation, distribution, fault tolerance, result consolidation, and even pagination.
That's right.
Wow.
There's even more to it.
Okay.
The broker leverages LinkedIn's internal D2 Zookeeper service for service discovery. This means it can dynamically track the list of available searchers for each partition, ensuring that queries are always routed to active instances.
So it's like an intelligent traffic cop.
A very apt analogy.
Constantly monitoring the road conditions and directing traffic accordingly.
And to further optimize performance, the broker uses sticky routing.
Oh. Okay, what is sticky routing?
This means that requests for a given member ID are always sent to the same searcher replica whenever possible.
Why is sticky routing beneficial?
It helps reduce the amount of data that needs to be transferred between the broker and the searchers.
Okay.
If requests for a particular member are always routed to the same searcher, that searcher is more likely to have the necessary data cached in memory.
Gotcha.
This results in faster response times and reduces the overall load on the system.
It sounds like they've really gone the extra mile to optimize for speed and efficiency at every level of the architecture.
They have.
This InSearch system is truly a marvel of engineering.
Yeah, it is.
But I have to ask, with all these moving parts, how do they ensure data consistency?
Yeah.
We've talked about replication, but how do they make sure all those replicas stay in sync?
That's a great question.
Yeah.
And it's a critical aspect of any distributed system to maintain data consistency. They use a technique called write-ahead logging.
Okay, so how does write-ahead logging work in the context of InSearch?
Before any change is applied to the actual data stored on a searcher, a record of that change, called a log entry, is written to a separate, highly durable log.
So it's like keeping a detailed journal.
Precisely.
Every modification made to the data.
This log is replicated across all replicas, ensuring that all copies have the same history of changes.
But how does this help with consistency?
If a searcher crashes or needs to be restarted, it
Okay.
can use this log to replay all the changes that occurred since its last known state.
Gotcha.
This ensures that the data
Right.
on the restarted searcher is consistent with the data on all the other replicas.
That's a clever approach.
Yeah.
It seems like write-ahead logging provides a safety net to prevent data corruption or inconsistencies.
It does. It's a fundamental technique for ensuring data integrity in distributed systems. In InSearch, it ensures that all replicas of a partition remain consistent, even in the face of failures or restarts.
All right, so they've tackled data consistency.
Yes.
But with all this focus on performance and scalability, haven't they overlooked security?
Not at all.
Okay.
Security is paramount in any system that handles private user data.
Yeah.
Especially something like messaging.
For sure.
Remember that the messages themselves are stored in encrypted form within RoxyDB. Only authorized users with the correct decryption keys can access the content of their messages.
So the encryption is handled at the data storage level,
Exactly.
preventing unauthorized access.
Correct.
Even if someone were to gain access to the underlying database.
It's end-to-end encryption,
Okay.
meaning that the messages are encrypted on the user's device, transmitted securely, and remain encrypted while stored on LinkedIn's servers.
Gotcha.
This ensures that even LinkedIn itself, cannot read the content of those messages.
That's reassuring to hear.
Yeah.
They've clearly made security a top priority.
They have.
Now, we've covered a lot of ground here.
We have.
From indexing and caching to partitioning and replication. It's an incredibly intricate system.
It is.
With a lot of moving parts.
Yeah.
But I'm still curious about how it all comes together in practice.
Well, in the next part,
Okay.
we can dive into some specific scenarios.
Yeah.
And we can discuss how InSearch handles different types of search queries.
Okay.
We can explore how the broker routes requests, how the searchers process the data, and how the results are ultimately delivered to the user.
Gotcha.
We can also examine the performance metrics that they've achieved and discuss some of the trade-offs they had to make along the way.
That sounds great.
Yeah.
I'm eager to see how this all plays out in real-world use cases. Okay, so let's shift gears a little bit and talk about how this all works in practice. Imagine I'm a LinkedIn user.
Okay.
And I want to find a message about a project deadline that's coming up.
Right.
What happens when I hit that search button?
Okay, so let's break it down step by step.
Yeah.
First, your search query, project deadline, is sent to the broker.
Right, the entry point for all search requests.
Remember, the broker is that intelligent traffic cop we discussed earlier?
Yeah, okay.
So the broker takes your query and performs that query rewriting step that we talked about.
Right.
It might add some operators to like refine the search, like requiring both project and deadline to be present in the message.
So it's making sure that the query is in a format that the searchers can understand?
Precisely.
Yeah.
Then, using its knowledge of the partitioning scheme,
Yeah.
the broker figures out which searchers are responsible for your messages, and then it uses that scatter-gather approach to distribute the query to all of those searchers.
Okay, so multiple searchers are working on my request at the same time.
At the same time, yeah.
Yep. Okay.
Each searcher checks its cached index for your member ID.
Okay.
If it's there, great.
Yeah.
It searches that index and returns the matching messages to the broker.
Gotcha.
If not, it goes to RoxyB, retrieves your messages, builds the index, caches it, and then performs the search.
Wow. It's impressive how they've optimized for both frequent searches and first-time searches.
It is.
Okay.
Now, the broker gathers all the results from the different searchers, combines them. It then performs that re-ranking step to make sure that the results are ordered correctly based on relevance. And finally, it applies your pagination settings, sending back only the requested page.
Okay, and all this happens in under 150 milliseconds.
For 99%.
For 99% of searches.
Of searches, yeah.
That's incredible.
It is, especially considering the complexity of the system and the fact that we're working with encrypted data.
Yeah, for sure.
It's a testament to their engineering and the thoughtful design decisions they made along the way.
This deep dive has been awesome.
It has.
As a software engineer, I'm always fascinated by how companies tackle challenges at scale.
Yeah.
And LinkedIn's InSearch is like a really, really cool example of innovative engineering.
I agree. They built a system that's not only performant,
Right.
but it's incredibly resilient and secure.
For sure.
And what's even more interesting is that they're not stopping there.
Yeah.
The blog post mentions that they're planning to expand the use of InSearch beyond just message search,
Oh, wow.
suggesting that they've created this versatile platform that can be adapted to various search use cases within LinkedIn.
That's really cool. So what does this all mean for our listeners, many of whom are software engineers themselves?
It's a valuable case study in building scalable and performance systems. It highlights the importance of understanding your data access patterns and optimizing for them.
Right.
It showcases the power of techniques like indexing, caching, partitioning, and replication.
Okay.
And it demonstrates how to leverage existing tools like Lucene and RocksDB in really innovative ways to solve very specific problems.
It's a reminder that sometimes you need to step outside the bounds of conventional solutions and build something totally new.
Completely new.
To meet these unique challenges.
Yeah, I think this deep dive leaves us with this thought-provoking question.
Okay.
As data volumes continue to grow and user expectations for speed and responsiveness increase, how can we as engineers build systems that are not only efficient today, but adaptable enough to handle the demands of the future?
Right.
LinkedIn's InSearch provides some compelling answers.
Yeah, it does.
And it serves as an inspiration for how to approach these challenges with ingenuity and technical excellence.
Absolutely. Thanks for joining me on this deep dive.
Of course, happy to be here.